So, welcome all of you to this course of lectures on electricity and magnetism. There will be around 20 lectures. The subject is vast. There are ever so many phenomena that come under this subject matter of electricity and magnetism, and 20 lectures are too short in number for us to discuss them. However, we know that this is only a supplement to what you are going to study in your classroom and the experiments that you are going to do in your laboratory. So, it is good for you to remember that what these lectures aim at is to provide you with the perspective, with an understanding, and the way one has to think in order to understand the subject matter of electrodynamics. Now, apart from gravity, which binds us to the earth, almost every aspect of our life is governed by electrodynamic phenomena. Starting all the way from atoms and molecules to chemical reactions, and then we have the mental processes, the biological processes, all the electrical appliances that you have in your home, in your laboratory, in your office, in your lab, in your classroom, all of them are governed by a set of laws which are called as Maxwell's equations, which summarize all of the known electrodynamics. So, to that extent, there is no other interaction which is more important for us, which is more essential for us in this particular universe, because even life would be impossible for us, impossible on this earth without electromagnetic phenomena. It is quite remarkable actually that although there are ever so many phenomena, all the way starting from atomic physics to, let us say, huge power stations and transmission lines that we see, all the electromagnetic phenomena can be summarized in a set of merely 4 equations known as the Maxwell's equations. So, let me write them down for you. You are already aware of them. The first equation is the so-called Coulomb's law, which tells you that divergence of the electric field is equal to the charge density divided by a constant which is called as the electrical permittivity or the dielectric constant of the vacuum. The second equation tells you that there are no magnetic monopoles, so which we write by saying divergence be equal to 0. The third equation is the famous Faraday's law of induction, which also gives rise to Lenz's law, eddy currents, so on and so forth, which tells you how a changing magnetic field, a magnetic field is changing in time, as you can see, is going to produce an electric field. So, here you should imagine that the magnetic field is the source and the electric field is the effect, whatever is being produced by the magnetic field. And the last equation is a generalization of the Ampere's law, which tells you how currents actually produce the magnetic field. So, that is written as mu naught epsilon naught delta E by delta T plus mu naught J. Here J is the current density which is produced by the moving charges, and the other current mu naught epsilon naught delta E by delta T is the displacement current, which is actually the changing electric field which can produce the magnetic field. Of course, this is not the end of electromagnetic equations, because these 4 Maxwell's equations have to be supplemented by what is called as the Lorentz force equation. Now, what is the difference between Maxwell's equation and Lorentz force equation? Maxwell's equations tell you how sources, namely charges and current densities, are going to produce electric and magnetic fields for you. On the other hand, the Lorentz force equation, which I am going to write, will tell you how the electric and the magnetic fields are going to act on a charged particle. So, that is given by F is equal to Q E plus V cross B. So, all in all, we have a set of 5 equations. The 4 Maxwell's equations that I wrote in the previous page, and the 5th equation that I have written now, which explain all the known electrodynamic phenomena. In other words, when we start a course like electrodynamics, here we have 2 options. Either we climb up all the way, understand phenomena as we go through by looking at various experimental facts, and then set up these equations one by one. Or if you were doing an advanced course, we would say that we will start with Maxwell's equations because we know them to be correct laws of nature. We start with the Lorentz force because we know that it is already verified experimentally to a great extent, and then we work out the consequences. Here, since it is an introductory course for you, since it is the ever first course on electrodynamics for you, what we shall do is to take the first viewpoint. We start with simple experimental facts. We start with simple mathematical techniques, try to build the whole subject matter of electrodynamics step by step. In other words, we are going to climb up the hill to reach the peak of the laws of electrodynamics rather than climb down the hill as we work out various applications. However, before we do that, as you might have noticed, if you were to go to the Maxwell's equations again, you see that these equations involve the kind of mathematics which you would not encounter when you looked at Newton's mechanics. In Newton mechanics, what you have is ordinary differential equation, whereas what you have here is a partial differential equation, a set of partial differential equations, and these partial differential equations involve the divergences, the curls, and so on and so forth. And therefore, what we should first of all do is to get our basics right. We should know what the meaning of this divergence is, what the meaning of the curl is, what is the meaning of the equation, for example, that curl E plus delta pi by delta t equal to 0. In other words, we have to understand, we have to pick up the basic vector analysis and the vector operations that we do. So, before we embark on the journey of learning electrodynamics, what we shall do is to take a short break, start with vector analysis, vector algebra. We develop all the basic mathematical apparatus that is required by us, and then we shall return to electrodynamic phenomena. However, before I do that, what I need to do is to set up my notations. So, let us start with the most basic prerequisite of everything that we have to do, and that is setting up a coordinate system. The charged particles are going to be located at various points if you are interested in a static case, or if you are interested in stationary magnetic fields, there will be steady currents which are located in various regions of space. If you are not interested in a steady situation, of course, there are charged particles which move from point to point. In order to discuss these phenomena, in order to discuss how they move, we have to set up a coordinate system. What we shall do is to start with the most well-known of the coordinate systems, namely the Cartesian coordinate system. The rectangular Cartesian coordinate system consists of a rigid scaffolding of three basis vectors which are orthogonal everywhere and which are universal. So, let me show them that now for you. So, I will draw a coordinate system. Let me label the axis. I have my x-axis here, I have my y-axis here, and the z-axis here. So, when I say that this forms a rigid scaffolding and the basis vectors are independent of the location, what I mean is the following. To start with, let me note the unit vector along the direction x by the notation I hat, the unit vector along the direction y, or that is along the y-axis by j hat, and the unit vector along the z-axis by the notation k hat. These are the three unit vectors which are orthogonal to each other, and they form my basis. When I say that I have a rectangular Cartesian system, what I mean is, if I take a point P here, and if there is a vector here, it could be the velocity vector and it is in this direction. In order to take the components of this vector, what I do is to look at the basis vectors written as the following, namely, my I is along this direction, j is along this direction, and k is along this direction. What do I mean by that? By that I mean that the unit vector I is parallel to the unit vector I here, the unit vector j is parallel to the unit vector j here, the unit vector k is parallel to the unit vector which I have originally defined. So, in that sense, the orientation of the unit vectors, for that matter even the relative orientation, does not change as I move from point to point, and this is what defines a rectangular Cartesian coordinate system. Therefore, what we mean is that if I were to denote it by I prime, j prime and k prime, I know that I prime is parallel to I, j prime is parallel to j, and k prime is parallel to k. Sometimes it is convenient not to use the notation ijk for these unit vectors, which do in fact form a basis, but we can also use the notation given by x prime, x hat, y hat and z hat. What do I mean by that? By that I mean that x hat is used interchangeably with I hat, y hat is used interchangeably with j hat, z hat is used interchangeably with k hat. Is that okay? What we shall do is to see how we can actually move on to other coordinate systems. The simplicity in rectangular Cartesian coordinate system is that the unit vectors do not change their orientation. Taking the components, taking the derivatives, evaluating divergence, curl, setting up differential equations, all these are extraordinarily simple. However, when we look at a given physical problem, Like for example, I am interested in the field produced by a point charge particle, or I am having infinite line charge with a uniform charge density lambda, and I am interested in the electric field produced at a point P at a distance d, for example, by this infinite line charge lambda. Now, if you look at this former case, namely the point charge, or if you look at the infinite line charge, what is it that you find? For the point charge, you find that there is a spherical symmetry. All that you have done is to choose a special point in the space, that is the location of the charge, whereas once it is done, all the directions in the space are completely equivalent. In other words, it is immaterial whether I am going to construct a rectangular Cartesian coordinate like this, or I am going to construct a rectangular Cartesian coordinate like this, or by any other rotation. They are all completely equivalent. In a similar manner, if I were to look at the infinite line charge lambda, you see what we have now is not spherical symmetry, but what we have now is a cylindrical symmetry. I have not only chosen a preferred point, that is, let us say the center of this very, very long line charge, but I have chosen a whole direction, the direction along which the line charge is distributed. Now, what I have is a cylindrical symmetry, because if I were to draw a cylinder of a given radius r, let us say, all points on the cylinder r are completely democratically to be treated with respect to the point charge lambda. For simplicity's sake, I could have taken this to be along the z-axis. In order to describe this kind of very special but frequently occurring situations, it is convenient for us not only to use rectangular Cartesian coordinate system, in fact, not to use rectangular Cartesian coordinate system, but to use what are called as the other coordinate systems, namely the cylindrical coordinate system and the spherical polar coordinate system. Now, I will start with the simpler of the two. What is closest to the rectangular Cartesian coordinate system is the cylindrical coordinate system. Then I move on to the spherical coordinate system, which is slightly more complicated. There is no great deal about these things because you people have already studied it in your course on engineering mechanics. So I am not going to delve into all the great details of this spherical polar coordinate system or cylindrical polar coordinate system, but we shall get into the bare essentials, whatever is required for our purpose in order to understand the laws of electrodynamics. Okay, what shall we do when we want to set up the cylindrical coordinate system? Let me draw the Cartesian coordinate system again. So what I have is the x-axis in this direction, I have the y-axis in this direction, and I have the z-axis in this direction. Now imagine for yourself that the xy plane is the horizontal plane and the z-axis is coming out of this particular plane. That is what we have. Now let me take a point, for example P. What I shall do is to not to give the coordinates of P in terms of x, y, z, but I shall project this P in the xy plane. So this is the projection of P in the xy plane, and then in the xy plane I am going to draw the distance at which this projection is going to lie from the origin O. Let me call this distance as rho. Now obviously when I look at the projection with respect to the origin O, this makes an angle which I shall denote by theta. So in the xy plane I have been able to set up two coordinates, namely rho and theta, and for any fixed value of rho, what I shall do is to draw a circle which will actually go like this, and theta will vary from 0 to 2 pi. So which I shall write here. So I shall say 0 less than or equal to theta less than pi. That means we have been able to completely characterize the projection of the point P in the xy plane in terms of two equivalent parameters, namely rho and theta. Rho is the distance of the projection from the point O, so clearly rho takes values from 0 to infinity, whereas theta takes values all the way from 0 to 2 pi as I have written earlier. Now what about the z-axis? No problem about that, because what we are going to do is to project the point P along the z-axis, and we shall retain the z-axis as it is, and clearly the z variable will take all the way from minus infinity to plus infinity. It can go all the way from minus infinity to plus infinity. Therefore I write minus infinity less than z less than plus infinity. So what have we done? Instead of going through the usual rectangular Cartesian coordinate system in terms of x, y, z, I projected my P to the xy plane, and in the xy plane I replace the variables x and y by two equivalent variables, please mind, namely rho and theta. You give me any value of rho and theta, I will be able to give you x and y. Give me any value of x and y, I will be able to give you the value of rho and theta, except of course at the origin, and that we shall be able to write down in the following equations, which is clear from the geometry. So how do we write? We simply write x equal to rho cos theta and y equal to rho sin theta and z is equal to z. So the new variables are therefore given in terms of rho, theta and z. Clearly from the geometry that we had in our earlier figure, you see what we have done is to erect a whole series of cylinders. That is what we did. For every given value of rho, there is a cylinder. You keep on moving along the z-axis, and then you change the value of rho, you draw one more cylinder. You change the value of rho, you draw one more cylinder. Eventually, you fill the space with a whole number of infinite number of concentric cylinders, and you locate the point on any one of those cylinders in terms of rho, theta and phi. That is what we have done. Therefore, it is an equivalent description. There is a small minor point which is of not any great interest to this particular course, but for the sake of completeness, we should be mentioning that, and that is, if I put rho equal to 0, that is, if I sit at the origin or if I sit along any point along the z-axis, theta is not defined. On the other hand, if I go and look at x, y, z, there is no such ambiguity. X, y and z are going to uniquely fix the coordinates, but that is a matter of not very great importance to us in this. Therefore, we need not worry about this particular aspect, but please remember that, because eventually when you write down the volume element or whatever, you might start wondering what happens to the volume element that you are going to write, the so-called integration measure. That is something that we have to remember. Now, having done that, once we introduce the new coordinates rho, theta and z, we have to introduce the analogues of I, j and k. We have to introduce the analogues of these, that is, I have to introduce a unit vector which changes only when rho is changed, which I will denote by the symbol rho hat. I have to introduce a unit vector theta hat. What does it do? I keep rho and z fixed, and I only vary my theta and ask how that vector is going to change. That I shall denote by theta hat. And in a similar manner, I have to introduce the unit vector z hat, which is identically the same as k hat, as we said earlier. And if we did that, then we have erected the coordinate system completely. We know how to go from one coordinate system to another without any trouble, and that we shall do in the next step. How do we do that? In order to do that, it is good to go back to the basic definition. And what is the basic definition? I will again write this. X is equal to rho cos theta, y is equal to rho sin theta, and z is equal to z. It is a redundant thing, but it is good to write that. Now, let me imagine that I have a point P in this coordinate system, and this is having the coordinates rho, theta and z, the point P. What I shall now do is to hold theta and z fixed. I will change only my value of rho. I ask what is the resultant displacement in the point P. That is not difficult to find out at all, because as you can see, the x coordinate will change by a quantity dx, which is given by d rho cos theta. The y component will change by a quantity which is given by dy is equal to d rho sin theta, and z of course will not be able to change, because we are only moving in the xy plane, because we are changing rho, which is defined only in the xy plane. Therefore, we shall write dz is equal to 0. That is what we shall do. So, since I know dx, dy and dz, and since we know that they are all along perpendicular directions, I should be able to write my infinitesimal displacement as d rho cos theta into I hat plus d rho sin theta into j hat. Well, how do I find out the unit vector? Calculate the magnitude of this infinitesimal displacement, divide it by the magnitude, and you get back your unit direction. So, I don't have to work it out. It is a very easy thing to work out. We shall therefore say that the unit vector rho is simply given by cos theta I plus sin theta j. Now, clearly, as you people can see, the direction of rho will change as we keep on changing theta because rho is always radially outwards in the xy plane. So let me show that for you here in the previous picture. When we come back to the very previous picture, you see my rho was defined here and it was a radially outward quantity. So if I am along the x-axis, rho is along the x-axis. If I am moving along the y-axis, rho is along the y-axis. If this theta were pi by 4, for example, rho would be along the direction that bisects this xy plane. Therefore, rho is going to change as I keep on changing my direction, which is indicated by this. In a similar manner, it is also not a difficult thing for us to find out what the theta direction is. The prescription is very simple. Hold rho and z fixed and simply change the theta. Well, what do we do for that? Again, we can write dx will simply given by minus rho sin theta d theta. What I have done? I have written dx is equal to rho d of cos theta, which is nothing but minus sin theta d theta. In a similar manner, dy is given by rho cos theta d theta, and dz of course is equal to 0 because the theta is also defined in a plane which is perpendicular to the z axis, namely the xy plane. Again, I can write down the infinitesimal displacement because of this in the point P, which we had defined earlier. And what will it turn out to be? It will simply turn out to be minus rho sin theta d theta I hat plus rho cos theta d theta j cap. That is what it is. Now, the way to find out the unit vector along the theta direction is to calculate the modulus value of this ds and divide this vector by this modulus value. So take this value, bring it here and put it here, then we would have done our job. So we shall do that, and if we did that, you will find that the theta cap is simply given by minus sin theta I plus cos theta j. So we succeeded in constructing the three unit vectors along the theta direction, the rho direction and the z direction. There is nothing much to do in the third direction, but for the sake of completeness, I will write z identically z equal to k hat. But at this point, it is good to pause and ask, what is it that we did geometrically? So let me write down the figure again. Since z-axis is a kind of uninteresting variable, let me restrict myself only to the plane here. So I have my x-axis here, I have my y-axis here, and I have my circle here. This circle is the projection of the point P, if you feel like, and this is my rho. So what is it that is meant by the unit vector rho? The unit vector rho is nothing but the unit vector which is radially away in this particular sense, whereas theta, if you look at the formula that I have written just here, is simply given by the tangent to this circle at this particular point. So as you people can easily see, rho and theta continue to remain perpendicular to each other. So in going over from rectangular Cartesian coordinate system to the cylindrical coordinate system, we did not abandon the orthogonality of the unit vectors. The unit vectors in the rectangular Cartesian system were orthogonal. The unit vectors in the cylindrical coordinate system are also orthogonal. The one and the only difference between the two coordinate systems is that the unit vectors, their orientation did not change as I moved from place to place, whereas as you people can see here, as I move along the circle, rho and theta continuously change their orientation such that they remain perpendicular to each other. Please also notice that in this particular definition, there is a specific preferred direction that has been chosen for theta, namely, theta would be positive if I went in the anti-clockwise direction, that is, I moved from x to y, and theta would be negative if I moved in the clockwise direction, which is the usual convention that we hold. So, what is the summary? The summary is that whenever you have a cylindrical symmetry, we will be able to use the cylindrical coordinate system to our advantage. It is characterized by three unit vectors, rho, theta and z. Rho is radially outwards in the xy plane, theta is tangential in the xy plane, z is simply parallel to the z axis or perpendicular to the xy plane. Once we have done this, it is clear from the geometry that if I were to move along the theta direction, so let us say that I moved a direction by a certain angle delta theta, then this arc length is nothing but rho delta theta. This is one and the only fact that we have to remember if we want to construct the line element, the area element, or the volume element. So given this fact, it is not difficult for us to construct the line element and the volume element at all, because we can immediately write that ds squared, which is the displacement which comes because of moving the point P to another point P by a small, by a very small distance, will be simply given by dx squared plus dy squared plus dz squared. That is what I did. All that I have done is to make use of the Pythagorean law. Let me show that for you again in terms of this coordinate system. So I have this coordinate system. I have z, I have y, I have x here. I have taken the point P here, and then what I have done is to project it. This is my theta, this is my rho, and this is my z. I move it from a point, this point which has coordinates x, y, z, to a nearby point, let us say P plus delta P. I have moved to this point. I am not interested in finding out what the change is in terms of dx, dy, and dz, but I am interested in expressing it in terms of rho, theta, and the z axis. That is what I am interested in, because rectangular Cartesian coordinate system is something that is familiar to all of us. But then we know how to write down dx in terms of the infinitesimal changes in rho and theta, dy in terms of the infinitesimal changes in rho and theta, and dz of course is given in terms of dz. So if I were to do that, it is very easily done, because now I am going to give independent displacements both in terms of rho and theta, unlike what I did earlier. Therefore dx will be given by d rho cos theta minus rho sin theta d theta. dy will be given by d rho sin theta plus rho cos theta d theta, and dz will be given by dz. So now let us plug these equations and find out what is the resultant expression that I am going to get for my length element. That length element will therefore be given by simply d rho squared plus rho squared d theta squared plus dz squared. Of course, if I were to move radially, you will move a certain d rho. As I showed you with the arc length in the previous diagram, here arc length is given by rho delta theta. Therefore, if you hold rho and theta fixed, and if you move along the theta direction, you cover a distance rho squared d theta squared. If you move along the z direction by a quantity dz, you move along the dz squared. Since rho theta z, x, y, z are both rectangular Cartesian, I am able to write it as orthogonal to each other. I am able to write it as d rho squared plus rho squared d theta squared plus dz squared. In a similar manner, I should be able to write down what the area elements are. Now suppose I am interested what the area element in the xy plane is in terms of the rho theta coordinate. Well, hold dz fixed and simply look at these two terms. In other words, the area element in the rho theta surface, let me not call it a plane at this particular point, will be simply given by rho d theta. In a similar manner, the area element in the rho z surface, the rho z surface actually correspond to moving on the cylinder holding the theta fixed. Therefore, my area element on the rho z surface is simply given by, from this you can easily see that it is d rho dz, and the area element in the theta z surface is given by rho dz d theta. So if I had an integration to perform, for example, in the theta z plane corresponding to a cylinder, you would be using this area element. Or if I had a function that you had to integrate freezing the value of theta and you had to vary only rho and z, you would use d rho dz. And on the other hand, if you had to integrate in the xy plane in the polar coordinates, which you are all familiar with, then you would end up with rho d or d theta. That is what you would do. In a similar manner, I should be able to construct what my volume element is. Well, it is simply given by the product of these quantities which multiply what? D rho, dz and d theta in my length element. Therefore, my volume element is simply given by rho, d theta, dz. So what have we done? We have not only constructed an orthogonal coordinate system in terms of rho theta z, we have found out how to measure the unit vectors, how to determine them. we have found out what the various area elements are in each of the two surfaces. There are three surfaces corresponding to rho theta, rho z and theta z, and we are also able to write down the volume element, and this will be very useful for us later when we try to determine the potentials, the fields, the forces and so on and so forth in electrodynamic phenomena. This should sort of conclude the discussion of the cylindrical polar coordinate system. What I shall now do is to get into the spherical polar coordinate system. The spherical polar coordinate system is also not any great complication for us once we get the geometry right. And the geometry for us is all familiar because of whatever we studied in geography. What is it that we did in order to locate various cities or places in geography? We characterize them not in terms of xy coordinate or for that matter cylindrical coordinates. We characterize them in terms of latitudes and longitudes. That is exactly what I am going to do right now. However, in order to be on firm ground, let us start with the rectangular Cartesian system again. So you have the z-axis along this particular direction, you have the y-axis along this direction, you have the x-axis along this direction, and I now write a point P. Now, when I am interested in the spherical polar coordinate system, as I told you, this would be useful whenever there is a spherical symmetry. Therefore, the first question that I ask is, what is the distance that this point P makes with respect to this origin? More often than not, this origin is chosen based on convenience, depending on the problem. If I am interested in the field produced by a point charge, the origin will be located at the center. If I am interested in the scattering of a charged particle because of a nucleus, like for example in the Rutherford scattering, the origin will be located in the scattering center, namely the nucleus. So there is a certain physical significance attached to this choice in a practical problem. So let me write this origin and I ask, what is the distance which is this point P is going to describe, is going to possess, and I shall denote it by r. Now what I shall do is to ask, what is the angle made by this point P with respect to the z-axis? So this angle will be simply given by the theta. Now let us again project the point P to the xy plane. Take the coordinates of the point P in the xy plane. I am not interested in the length of this projection because I have already given the total length. I will only ask what is the angle made by the projection with respect to the x-axis, and I shall denote it by phi. So what have I done? That shall be indicated by a figure now that I am going to write in terms of a sphere. So I have a sphere here and there is a point P here. For the time being, if I imagine that I have my radius fixed, so these are my latitudes and these are my longitudes. So if that is what I am going to write down. So let us say that I am taking a point P here. I am asking what the angle made by this particular point P is with respect to the z-axis. That is what I am asking. Now of course I can complete the circle at this particular point. So this is of course my equatorial circle. That is what I have here. This is my origin, and if this is the point, what I am asking is, if I project to the xy plane, there is going to be unit vector in this direction, and I am asking for the angle phi made by the point. In other words, the variable theta is nothing but the angle that the point P makes with respect to the north pole. The angle phi is nothing but the angle made by the projection with respect to some preferred direction in the equatorial plane. That is all what we are doing. So what does it mean? Theta equal to 0 would correspond to the north pole. So let me write it down. It will correspond to the north pole. Theta equal to pi by 2 would correspond to equatorial plane. And theta equal to pi would correspond to south pole. This is for a given value of r. Now imagine that I keep on changing my value of r, starting from very, very small values of r, namely r equal to 0. What have I done? I have filled this space with a series of concentric spheres. So when I describe my location of my point in terms of spherical polar coordinate system, I first ask at what distance is it from the origin. So that will be given by the distance r. And then I ask what is the angle made by that with respect to the z-axis. And the z-axis is the line that connects the origin with the north pole of the sphere, and that angle will be denoted by theta. Then I project the point onto the xy plane, which is the equatorial plane, which of course it depends on where the point is located, and ask what is the angle made with respect to the x-axis, and that will be denoted by the phi. So all that we have done is to take over the concept of whatever we have studied in geography, made minor changes in our notation, and introduced this coordinate system. So in the spherical polar coordinate system, the variables are given by r, theta, and phi. Once I fix my values of r and theta, one can easily see that the freedom in phi corresponds to moving along this circle. This circle has a radius which is given by rho sin theta. However, phi itself can take values going all the way from 0 to 2 pi. So if you remember that, we shall be able to write down the ranges for r, theta, and phi. So what are they going to be? R will take values 0 less than or equal to r less than infinity. Theta will take values 0 to pi. Remember, we said that theta equal to 0 corresponds to the north pole, theta equal to pi corresponds to the south pole. That is the farthest that you are able to go. Therefore, we write 0 less than or equal to theta less than or equal to pi. Phi, of course, shall move on a circle which is in the equatorial plane. Therefore, we write 0 less than or equal to phi less than 2 pi. I have been somewhat extra careful in writing this. I did not write less than or equal to 2 pi because we all know that we identify phi equal to 0 with phi equal to 2 pi, because when you complete the full circle, you come back to your original point. If you people were to look at a globe in your house and look at the radial direction, the theta direction, and the phi direction that I have defined, you can easily check that the three directions are mutually perpendicular to each other. The variation in the theta phi restricts you on the surface of a sphere, whereas the variation in r is going to take you out of the surface of the sphere. So even without drawing any figure, it is clear that the unit vector in the direction of r has to be necessarily perpendicular to theta and phi. For convenience sake, if you were to look at the equatorial plane, for example, so this corresponds to the origin, z is equal to 0. My theta will be everywhere along the minus z direction, because I said if I were to draw a longitude, it will be pointing along the minus z direction, whereas my phi will be moving along the curve. So thus we see that theta and phi are also perpendicular to each other. This is not only true of the equatorial plane, it is true everywhere. In other words, all that we have done is to do a little bit of a minor generalization. It is not too great a generalization. Again, from cylindrical coordinate systems to spherical polar coordinate system, where we have three orthogonal vectors. So if we could only construct the unit vectors in the direction of r, theta, and phi, then we would be home. We would write down the length element, we would write down the various area elements, we would write down the volume element, and then whatever we would have to do, like for example setting up the divergence or curl or gradient in these coordinate systems, can be easily done. Speaking algebraically, it is no great complication. In fact, it can be worked out geometrically also. But let us look at it algebraically, because geometrically you can work it out by drawing nice area elements later. So again, let me rewrite x, y, and z in terms of r, theta, and phi. So from geometry, it is clear that x is simply given by r sin theta cos phi. Y is simply given by r sin theta sin phi. And z is given by r cos theta. Theta is the angle that the point P makes with respect to the z axis. Therefore, x and y lie in a plane perpendicular to that, which is the reason why I have r sin theta and r sin theta in both these places, which is essentially the value of rho. Cos phi and sin phi gives you further the projections along the x axis and the y axis. That is what I said. It is a slight generalization over what we did in the case of the cylindrical coordinate system. If you remember that, what do we do? Well, hold theta and phi fixed, vary r, and find out what your corresponding change in the point P is. So let me write that down. Theta, phi fixed. When you keep theta and phi fixed, you either inverts the sphere or outside the sphere depending on the direction in which you move. and in that case my x component would change by a quantity dr sin theta cos phi. The y component would change by the quantity dr sin theta sin phi, and the z component would change by a quantity dr cos theta. In the cylindrical coordinate system, when we moved along the rho direction, my z component did not change because it was in the xy plane, but when you move radially, all the components are going to change unless you are on some special points. For example, if theta equal to 0, you are along the z direction, you move only along the z direction, the x and y components would not change. But since we are interested in a general point P, all the three components are going to change. In other words, the displacement of the point P, which I shall again write, will be simply given by dx I hat plus dy j hat plus dz k hat, where dx, dy, dz are written in these three expressions. Now, all that we need to do is to take the modulus of this vector displacement and then divide the displacement vector by that. So, in other words, my r hat or r cap is simply given by ds by mod ds. Well, if we substitute, what are we going to get? We are simply going to get that it is given by sin theta cos phi I hat plus sin theta sin phi j hat plus cos theta k hat. As a special case, imagine that you are sitting along the x axis and you are moving radially. That means you simply move along the x axis, which is indeed correct, because if I put theta equal to pi by 2 and phi equal to 0, sin theta sin phi vanishes, cos theta vanishes, and only sin theta cos phi survives, that is equal to 1. R is parallel to the x axis. If I sit along the y axis and move radially, it is equivalent to moving along the y axis. Indeed, theta equal to pi by 2, phi is equal to pi by 2. Therefore, the coefficient of I hat vanishes, coefficient of k hat vanishes, only the coefficient of j hat vanishes, and that is equal to 1. And in general, if you were to sit anywhere on the sphere and move radially, this is the distance that we would be moving. So, the unit vector is simply given by this, and you should again check for your own sake that modulus of this object is equal to 1 once again, so that you are 100% sure that you have not committed any mistake. The construction of theta and phi is also not very difficult, because we have sort of evolved a general procedure, although I did not explicitly mention it. So, how do I find out what the theta vector is? Well, hold r and phi fixed and just vary theta. Remember, x is given by r sin theta cos phi, which tells you that dx will be given by r cos theta cos phi d theta. In a similar manner, dy will be given by r cos theta sin phi d theta, whereas dz will be given by r minus r sin theta d theta when we move along the theta direction. So, we found out dx, dy and dz when we varied only theta and held r and y fixed. So, the displacement will be given by r cos theta cos phi I plus r cos theta sin phi j minus r sin theta t k. That is what we have. Please multiply these quantities by d theta, which is missing in the expression. Again, all that we have to do is to take the modulus of this vector and then divide ds by this modulus of this vector and get the theta direction. Well, it can almost be written on inspection. It will turn out to be cos theta cos phi I plus cos theta sin phi j minus sin theta k. I mentioned that if we were to sit in the equatorial plane, the theta should be pointing along the minus z direction, because that is how the longitudes come when you start from the north pole. That is substantiated by this expression, because if I put theta equal to pi by 2, the components along the I and j vanish, the component only along the k survives, and there is a correct minus sign sitting here. Similarly, you can look at what the value of theta should be at various other points on the surface of the sphere. it will agree with it. And all that we are left to do is to construct the unit vector in the direction of phi. The unit vector in the direction of phi is somewhat simpler because we know that the z component does not depend on phi. Z was simply given by r cos theta. Therefore, all that we need to do is to worry about the changes in the values of x and y. Indeed, phi is the angle that you produce as you move in the xy plane on that circle of radius r sin theta. That is something that we already mentioned. Therefore, what is it going to be? My dx for this particular case will be then given by r minus r actually sin theta sin phi, and dy will be given by r sin theta cos phi. I have to put a d phi here and a d phi here, because d of sin phi is cos phi d phi and d of cos phi is minus sin phi d phi. That is what we have. Dz is identically equal to 0. So, the displacement is entirely in the xy plane along the tangential direction, exactly like what happened in the case of the cylindrical polar coordinate system, except that there the radius was denoted by rho. Here the radius is denoted by the quantity r sin theta. So, if you remembered it, your phi hat will be simply given by minus sin phi I hat plus cos phi j hat. So, without doing any great complicated algebra or manipulation, or for that matter in involved geometric construction, we have succeeded in constructing all the 3 unit vectors. These 3 unit vectors have a complicated dependence as they move on the surface of the sphere of any radius. They keep on changing their orientation, but even as they keep on changing their orientation, they remain orthogonal to each other. That is something that can be verified explicitly. I am not going to work it out for you because I have already given you the expression for all the 3 unit vectors. Please go back and verify that r dot theta equal to r dot phi is equal to theta dot phi is equal to 0. That is something that has to be verified. In other words, what we have done is to erect locally orthogonal coordinate systems. They are not globally orthogonal. They keep on changing as I move from point to point. That might sound like a disadvantage, but on the other hand, the advantage is that when there is a specific symmetry, this will be particularly useful. Now, before I wind up the discussion of these coordinate systems, because I have discussed practically whatever is required for this course, because these are the only 2 coordinate systems that I am going to use throughout all these 20 lectures or so that I am giving. There is one more point that we have to make, and that is about the sense or the handedness of the coordinate system. That is very, very important, because if you go back to the Maxwell's equation, we have equations like curl of B is given by mu naught J, let us say. I have dropped the time dependent term. Here the right hand side, the current density is a polar vector, whereas the left hand side involves a curl. Very soon we will see, when I do the curl operation, when it acts on a polar vector, it is going to give an axial vector. When it acts on an axial vector, it is going to give a polar vector. And in order to define what is a polar vector or an axial vector, and to steer clear of troubled waters, what we have to do is to define our sense once and for all. So let us do that. That is something that all of us are familiar with, but let us be very, very explicit about that, and let me draw the coordinate system again. I have the x-axis, I have the y-axis, and I have the z-axis. Initially I told you that when I draw these x, y, z, they are mutually orthogonal to each other. That is not enough in order to define the sense. What we shall now further stipulate is that this z-axis is further characterized by an additional relation. In order to specify the additional relation, let me write the unit vector I here, let me write the unit vector j here, and let me write the unit vector k here. We now demand, that is an additional requirement that we are going to make, that I cross j must be equal to k. In other words, a positive displacement along this z-axis, which I am going to achieve, should come from I cross j. And what is the geometric meaning of the cross product of I cross j? If you have, for example, a screw which turns all the way from the x-axis to the y-axis, let us say anti-clockwise direction, the pitch should be positive, that is, you should move along the positive z direction. On the other hand, if you have a screw which turns from the y-axis to the z-axis, then that is actually like unscrewing the whatever your nut or whatever it is, then you move along the negative z direction. So we have defined the sense. You could have perfectly legitimately, perfectly legally used the other convention. You could have demanded I cross j equal to minus k. That is, I will not put the z-axis outside the plane, but it shall come outside the plane, all right, but below and not above. That would define what is called as a left-handed coordinate system. There are actually textbooks in physics which were written earlier employing the left-handed coordinate system, but by now it is a universal convention to use the right-handed coordinate system, and that is what we have, and that is what we shall stick to. Now, this handedness is not lost when we go from the rectangular Cartesian coordinate systems to the other coordinate systems. As an example, you people should work out and check that in the cylindrical coordinate system, rho cross theta is indeed given by the k. That is how it is. In a similar manner, you can go back and check in the spherical polar coordinate system that r cross theta is equal to phi. That is, although I am going to keep on changing the orientation of my 3 unit vectors, the basis vectors as I move from point to point, this relation of right-handedness will not be lost. By the way, in completing this discussion of these coordinate systems, I should also mention that whenever the basis vectors, these unit vectors analogous to ijk, they remain global. They do not change their orientation from point to point. That would be what is called as a Cartesian coordinate system, whereas the minute these basis vectors acquire a dependence on the point itself, those coordinate systems are called curvilinear coordinate systems. No surprise about that, because when we moved on the surface of a sphere, we were actually moving either along the latitudes or along the longitudes. When we erected the cylindrical coordinate system, we were actually moving along the circle. We were not moving along a straight line. Whereas in a Cartesian coordinate system, which is not curvilinear, what is it that we do? You find out whatever displacement you want by 3 linear displacements and not curvilinear displacements. So let us remember that a curvilinear coordinate system is one where the unit vectors have their orientation which changes from point to point. Of course, we could have a curvilinear coordinate system which is more complicated than what we have. The 3 unit vectors need not be orthogonal to each other. That would be a very, very general coordinate system. For that matter, you could have such a thing even in a plane. For example, this would be an example of what is called as an oblique coordinate system, but we shall not deal with curvilinear coordinate systems which are not orthogonal, nor shall we deal with oblique coordinate systems. We shall deal only with orthogonal, either rectangular Cartesian coordinate system or the curvilinear coordinate systems. In fact, we are going to restrict ourselves either to cylindrical or spherical in most of the cases. Fine. After having said that we are going to look at these coordinate systems, this is not the end of the tale for us, because it might so happen that there is a certain phenomenon. You are interested in finding out the potential because of the charge distribution. Let us say that there is a charge located one located here, there is a charge Q2 located here, there is a charge Q3 located here, there is a charge Q4 located here. Let us say that they are all distributed on this plane. There is no complication about that, and each of them is a physical point. But on the other hand, if I want to give it a mathematical description, I have to give their positions. So even if I were to restrict myself only to rectangular Cartesian coordinate system, I will have to erect one coordinate system. So I shall call it x, I shall call it z, this will be the y, this will be the x. Now with respect to this coordinate system, I will have, for example, a position vector which I shall call r4, because I am going to measure the location of each of these charges. The charge Q3 is describing a position vector r3. The location of charge Q1 is simply given by r1, and the location of some q, any arbitrary generic point, will be simply denoted by r. Now the question arises whether there is any preferred choice in having this point as the origin. The answer is obviously no. There is no great reason, unless of course there is a special symmetry consideration, but right now we are not interested in the symmetry consideration. It is perfectly possible that you could have chosen a coordinate system which starts at this point, the z-axis would be in this direction, the x-axis would be in this direction, and the y-axis would be in this direction, z, x and y. Now, not only that, there is no reason why the new coordinate system should in fact be parallelly displaced with respect to the original coordinate system. Let me display that in the next figure. So, let us say I have a coordinate system which I will denote by S1. What I shall do is I will not rotate my coordinate system at all, but I shall move the origin and all the three coordinates parallelly. So, this is O, let me call this as an O prime, and now I will erect another coordinate system, let us say. So, this is my x prime, this is my y prime, this is my z prime. On the other hand, what I can do is, I can move it to another point, let us say somewhere here, this is my O double prime, and what shall I do? Here I shall erect a coordinate system which is still rectangular Cartesian, but then what do? I move from this point O to O double prime, and I don't simply keep it there rigidly, I rotate it by a certain angle theta. Therefore, if my original z-axis were here, my z double prime is here, it makes an angle theta with respect to the z-axis. So, what am I saying? What I am saying is that if you give me one rectangular Cartesian coordinate system, I shall produce an infinite number of them. How do I produce an infinite number of them? By translations and by rotations. And that is something that we shall do continuously, because we need to have a meaningful dictionary with respect to various observers who are going to do various observations. Somebody says the force had a component, for example, 3I plus 4j plus 8k. Force on a charged particle because of the star distribution, which I wrote earlier. Some other observer tells me, no, this is wrong. The force had a magnitude which was simply given by, let us see, 3 squared is 9 plus 16, 25 plus 25 plus 64 is 101. Let us, 25 plus 64 is 89. Root 89, let us say, along the k direction. Suppose somebody said that. Now, there is absolutely no contradiction between these two, although they might appear to be giving two results which don't agree with each other, because they might have actually chosen two different coordinate systems. We do not want a quarrel between two observers who have chosen two different coordinate systems, either in terms of the location of the origin or in terms of the orientation, the relative orientation. Therefore, if we know how to go from one coordinate system to another coordinate system, either under the shift of the origin, that is called translation, or by rotation, then we will be able to compare results performed in various coordinate systems, and we shall take that up in the next lecture.